All right, let's get started. So, um, I've set up a small port of the lab, and not really configured anything yet. Just sort of popped in all the modules that you'll need. Um, so we always need a power supply, and I always suggested you put that in the top left quadrant. So we have our power supply here. Then we're also going to use a synchronous motor generator, and I put that in the rightmost module, but doesn't need to be there. Again, these can be in anyone as long as it fits. And then in the center, I've got this prime mover dynamometer. And I'm just using a really basic one. We can use the 4-quadrant prime mover dynamometer, but we don't need to be that sophisticated. So we can go with a standard prime mover dynamometer. And then down over here, I've got my data acquisition, my 4-channel data acquisition. And then I have my resistive load. And you'll see why we'll use the resistive load. It's basically to help us adjust the DC field current, but you kind of get the idea. Now, I have my power supply that I can grab my 24 volts over here and run it over there. But if you recall, if I scroll down to the bottom, I do have sort of this built-in 24 volt 3 amp power supply. And so sometimes, and maybe in this lab, it might make sense to actually use this one so you have less wires crossing over. So I just use that 24 volt output. And then I just daisy chained off of here. And it doesn't matter because this is just a common node. So I ran my 24 volt over to my prime mover dynamometer. And then I just jumped off that common node, and then I fed power into my data acquisition system. Okay. So those are the two that are going to require 24 volts. You need the 24 volts to display properly over here and to get a little bit of basic control. But since we're configuring this as a dynamometer, and let me zoom in just a little bit, you can see the toggle switch on this device is flipped over onto dynamometer. I can go ahead and I can actually have this act as a load. So since we're operating this as a synchronous motor and not a synchronous generator, the motor converts electrical torque to output mechanical power or mechanical torque. And what that means is that I need to have some sort of mechanical load. And these dynamometers act as mechanical load. And this is sort of an eddy current dynamometer, which basically you can circulate some eddy currents inside the motor and it generates heat. And then that heat is equivalent to the amount of torque that is produced or required by the machine. So that's going to be my load. So remember, when you're connecting these, you got to lower the front panel and you've got to go ahead and connect the wire. Shows as a wire, but it's actually a belt. And this is how you would be in the physical lab. You have the 2 pulleys over here, and then you have a belt tension in the center. And so when you connect these two, you actually will go ahead and have, you'll actually have a taut belt. So we'll rotate and close the lids because now we actually have to start connecting things. And the way to connect these things is the same for all parts of the lab. Let me see if I can drag the lab part over here. So, over here in step 3, you'll see a configuration over here. This is if you were limited and you wanted to really minimize the number of wires that you have. This is called the 2-watt meter method to go ahead and measuring actual 3-phase power. We don't necessarily need to do that. We can actually go ahead and use the 3-watt meter method. So we're going to go ahead and rebuild this with the 3-watt meter method here. And then we're going to go ahead and measure the current. So just be careful when you annotate your figure. Let me show my annotations here. Let's see. This is going to be the voltage across this terminal here is E1. Then I have E2. It's hard to do with a mouse versus a pen. And this is E3. And then each one of the currents is going to be measured here. This is going to be I1. This is I2. And this is I3. So the AC currents coming up from each of the phase are going to be I1, I2, I3. And the advantage to doing something like that is it just makes a little more sense when we're doing phase shift calculations, or if we're trying to calculate power factors. We measure the voltage and the current, the difference in angle between the two. Over here, we actually are playing around. We're swapping things around a little bit. Notice these pluses and minuses are different here. You have plus, minus, minus, plus. So that's how you can use a 2 watt meter method to do that. We're using the 3s, so we don't have to worry about plus minuses. We can set it up correctly. And then the last thing we're going to have is this is going to be I4. So E1 measures the phase 1 voltage. I1 measures the phase 1 current. E2, I2, voltage and current for phase 2. E3, I3, voltage and current for phase 3. And then I4 is this current, this DC current, that's going to go from over here, and it's going to feed in to our synchronous motor. And why do we want to do that? Because the huge advantage to synchronous motors, let me clear the annotation. Oops. The huge advantage to a synchronous motor is you have a constant speed, and you can vary the amount of current going into the motor based on how do you want this machine to operate. Do you want it to operate under overexcited conditions or underexcited conditions? You get to take the pick. And the more field current we have over here, the more excited the machine is. And right at this lowest level, the current to this point over, let me go ahead and annotate that again. So from this minimum point over, this is an overexcited machine. This is when you have more current than is what's necessary to match to provide the magnetic energy. Over here, it is underexcited. Sorry, this is hard to write with a mouse. And under this condition, you actually have too little field current to maintain the magnetic field that is necessary. So the current goes up in that case because you're pulling reactive power from the grid. In the case of overexcited, the current goes up because, again, the same thing, you're providing more current, more magnetic field than what is necessary for the machine so that you're exporting reactive power. Right here at the bottom, right when that reaches that medium point or minimum point, is when we have unity power factor. And what you're going to see when you do that is you'll notice that that confirms over here. This is going to be the reactive power, and it's going to be continuing to as you increase the field current, the reactive power is going to drop until such time that you've got so much field current that now the reactive power is going to go up. So this is negative reactive power, and this is positive reactive power. And so what we're going to do with the lab is basically validate these curves. We're also going to go ahead and do a couple things with just checking some starting torque, but that's kind of the simple stuff. So let's get started in wiring it. So again, I'm going to go ahead and wire this for my 3 currents going in. That's 1, 2, and 3. Now I've got to continue that current to the load. So I have 1 current going here. I have another one going here. And my last current goes here. So now I've got the 3 currents being measured properly. I've got to measure the voltages so I can calculate the power correctly. So I'm measuring that one's going to go to phase 1. That one's going to go to phase 2. And this one goes to phase 3. And then all the voltages I'm trying to monitor are phase to neutral voltages. So I go from neutral to the negative of the meter with E1. Same thing with E2, but I'm just going to drop it right on top. And same thing as E3. Did that connect there? Sorry about that. Okay. So the last thing I'm going to do is I'm going to go ahead and set up the field current. And what I'm going to do with my field current is that has to be a DC current, right? So I'm going to take the fixed 120 volt DC, which means it's going to be over here. So I'm actually going to drag that current from over here. And if you recall from the diagram, and let me bring my diagram back up, I want to make sure I have the capability of adding an external resistor in there, this R sub F. I already have a rheostat located right here, but I really want to choke down the amount of current going to the unit. So I'm actually going to go ahead and run it through the resistors. So I've got this current going to here. This current is returning from the COM of that value. And then finally, this one goes all back to neutral. So that's very busy, but that's the basics of wiring this particular circuit. Now, there will be cases where we have to short out this resistor or open circuit it, but right now, you kind of get the idea about it being, sort of set that way. I think in the first step, we're going to go ahead and short circuit it. So let's just put the short circuit wire like that. And we'll just have to delete that wire or drag it over into the other side whenever we want to bypass it. So now we've got our DC, our DC measurements. We have the currents. The only thing that we need to measure is speed and torque. Well, if you look at the prime mover that we have over here, dynamometer, you have a torque output and a speed output. So I'm going to run this to my DAC. Where it says terminal 7, you see it says torque. And I'm also going to run speed over to terminal 8. And I need to make sure that everything is sort of, properly grounded. So I have to run my analog out to my ground reference over there. That's kind of one that trips people up, but essentially it's outputting a voltage. And so again, you need a potential difference. And so you just have to reference the voltages to the same point, and that's all we're doing. We're running them to an analog common ground. Here is my Y-connected machine. The load, I have a Y-connected source, a ton of wires in here. And now I'm ready to go through the lab. So I will pause here to give you all a chance to see if you have any questions. Any questions? Or do you need a few minutes to catch up and do your wiring? I can't see anybody's face, so I'm kind of left with just a guess. Thank you, Rita. Thank you, Arthur. It's always useful to see people's faces to see if they're actually, biting their lips or if they're actually understanding the stuff and able to wire it. So I kind of need some feedback here. Do people want to spend a little bit of time wiring it, or do they just want to proceed with the lab?
Hey, Paul, where does the second power lead go? The one that kind of goes off the screen?
The gray one's right over here.
Yes.
So if you go all the way to the bottom, there is a separate 24-volt AC
Okay.
power supply here.
Okay.
So I'm just grabbing that from that point there. It doesn't matter. I just grabbed it over here because, as you can see, the wiring gets a little busy here.
Right.
So if you don't like that, you do also have the 24-volt that's available to you here, right? That
Right.
either point works perfectly fine.
Okay. Thank you.
What do you think, Bolt? Should we pause and let you wire it up, or soldier on and start working through the parts of the lab?
I'm all wired up.
Okay. Anybody want to start going with the lab, or anybody want a few more minutes to wire?
I think I'm ready.
I'm okay to start.
Okay. Well, since we're ready to start, let's flip the switch, crank it up. And when we run it to 100% power, you should see that this machine spins, and it should get really, really close to 1800 RPM. This thing takes a long, long time to get to 1800 RPM. You see it just kind of gimps along a little bit. 47, 48, 49. It should eventually get to 1800 RPM. I'm not sure why it's taking so darn long for it to get to 1800 RPM, but it should eventually get there. So, I mean, this is a synchronous motor that should run at that speed. I don't know why, other than, maybe it's got some goofy results. I'm not sure. But again, that's based on the dynamometer here. And yeah, so as you crank this up, is anybody having any issues with this thing operating as shown? Should all be rotating. Mine says 1749. Again, if you're in the lab, it was rotating at 1800 RPM exactly. I'm not sure why, because it doesn't make a lot of sense to me why it's running at 1750. But again, who knows with some of these goofy software things, hard to predict. Also, if you're having a problem, it's the dynamometer load control, we're going to want that to be manual, not external. External would be an output from our DAC. So we want that to be here. All right, let's start metering things up. So I've got 3 currents. I'm going to have those turned on. I've got 3 voltages. I want those on. E4 is not connected, right? So I got to turn that off. We'll click that off. I4 is going to be measuring current, but that's a DC current, right? Not an AC current. I also am measuring torque as well as speed. And eventually I'm going to be measuring power, but I'm not going to be measuring power for one single phase because I'm using all 3 meters to measure the power going to the synchronous motor. I've got to add all those up. So I click OK, and now I'm getting the power once I've got it set up. I'm going to do the same thing over here. Again, I want 3-phase power, but I want this to be reactive power. And turn that on. And the only reason why it's not displaying anything is because I'm not set up in continuous refresh. Okay. Any questions on that? Because we're getting fairly balanced here. There's no DC because this switch is open. It says 1748, so that's reasonably close to what it's indicated. Again, I don't know why it's not running at that value. Because if I look at the electrical frequency, it should say 60 hertz. But I'm not sure why that's running at 1750 RPM. It should be running at 1800 RPM. That make a lot of sense to me. All right, so I'm going to kill the switch, and you'll see that thing slow down. So let's go back to the lab, because the first part of the lab is in the meeting, we're going to make sure the torque correction factor of the torque meter is enabled, blah, blah, blah. For information, 2 operating modes is non-corrected and corrected. Torque is measured by the torque measurement mechanism or the mechanical power using this. In the corrected mode, the measured torque is corrected to compensate for errors due to friction in the torque measurement. Okay. So let's go back over here and let's make that, I think it says make it corrected. Yeah. The corrected torque is indicated. All right. So the first thing we're going to do is we're going to set the exciter switch to the closed position and turn the exciter knob fully clockwise. So this is here, closed position. Wrap that all the way around. And we'll stop the motor here. Now I'm going to flip the switch, and then hopefully this thing will start to spin, if it's able to. Now, you can see this is not able to start spinning. And the reason for that is it's a little bit of a simulation thing because we were able to get it down in the lab. So let's see if we can back this off a little bit and see if we can start to get. Oh, wait a minute. I'm sorry. No, I'm bypassing the resistor here. Putting that back on. Why doesn't this thing want to spin? Because in the lab, we were able to get it to spin. Let me turn this to minimum. Let me toggle the switch. So for the first part, you can't actually get it to spin. It does not actually start spinning with that. So your starting torque here is NA. It does not work, right? We cannot start the synchronous machine when our field winding is closed. And I think that that's a problem with the simulation. So you should be able to do it. And in lab, we got about 0.6. We were unable to do so in the physical lab. And again, I think that that's just a simulation error. Okay, so now we're going to go on the synchronous, set the exciter switch to the open position and record the torque. Let's see. This says 0.328. That's all I have for starting torque. That seems really low. Let's go back to the brake here and let's turn this to the maximum. And let's see if it's able to maintain some speed. It may not be spinning at 1800 RPM, but let's see if it'll actually be able to maintain some rotational speed. If this goes to 0, then that means that there's too much torque on the machine. So it looks like it's stable. Go ahead.
For that, aren't we supposed to have the exciter switch all the way turned up? Because I do have 1800 RPM, but my torque says 0. So
In the second part of the lab, this should be the exciter switch is in the open position.
isn't that all the way open? Like all the
Open's
way
down
cranked up?
here. All the way open. Open is down here. This is the switch.
Gotcha.
Okay. And it doesn't matter my exciter position because if this is open, this rheostat's not in service.
Okay.
Okay. So for the lab, this would be NA. For this one, I can see that this is actually capable. Now it's not doing great, right? It's only running at 1900 RPM, but I'm getting 2.166 Newton meters of torque capability there. And that would be our starting torque. That's the amount of torque. I think that that's the maximum I can go to here. I might be able to get a little more. Yeah. That's the maximum torque that I can get.
Oh, I got 3.
You get 3?
Yeah.
Well,
Oh, now it's dropping back down. Now
well,
it's
you
at
got to make sure the
1.9.
speed, you got to make sure the speed is stabilized. Has your speed stabilized? Like my speed is stabilized to 199 RPM.
Okay, yeah, it finally settled. It's at 199 RPM, but I'm still at 1.9 torque. Interesting. Everything else seems the same.
Huh, maybe you're running a fancier simulation than mine is because you've got this in the open position here.
Yes.
Okay. Okay. Well, I don't know.
Yeah.
All right. So in the real world, this thing is running at a lot of torque and a lot of load. This would be a very unhappy machine. It'd be overloaded. So let's turn this all the way off. Let it spin up to its synchronous speed, and let's just give it a chance to cool down. That's essentially what the motor is doing. When it's running very lightly loaded, you have fins on most motors, and that helps with cooling of the machine. So you're actually getting a little bit of cooling here. So you won't necessarily be able to answer that question in terms of, what the torque is, but, you kind of get, you get what you get. So, yeah. So we've got our minimum torque. We're going to skip through. Now we're running at 1749 RPM. Okay, this is lightly loaded. Now I'm going to go ahead and close this switch. And the reason why I'm going to close the switch is because this is basically running like an induction machine, right? When this is open, there's no DC field host, so there has to be an induced field. So that's why it's running at 1749, because it's running like an induction machine at a slip. When I close this machine, watch what happens to my speed. Right at 1800 RPM. Because now the two magnetic fields have to operate at the same exact speed. And because this is running at DC, this actually has to go to 1800 RPM. Okay. So that's the reason why it was not running at 1800. It was running at 1749 because it was operating as a synchronous machine or induction machine. So should be able to answer that question. Now it says vary the exciter knob between min-max position to vary the field current. You can go ahead and change that. I'm going to go ahead and help you get started on step number 9, which is to vary the field current from 100 to 800 milliamps. So let's bring up this. And let's bring up this. And let's see if I can put them side by side. And I'm going to move way over here. Okay, so this is, I want to start off at 100 amps, right? Or 100 milliamps of current. And as I increase this, watch what happens. My current goes up, not down. So what I've got to do is take this wire and, oops, I'm going to turn on one switch first. I'm going to turn on this 1200 amp first, or 1200 ohm first, because when I take this wire out, it's going to interrupt the DC. But now that this resistor is closed, it shouldn't give me any problems. So delete that wire and watch the current goes down almost exactly to 100 milliamps. Let me tweak it up just a wee bit. I guess it's close enough for me. Okay. So now I'm going to record my line current, which is the value over here, my field current, which is over here, my torque, my speed, and I'm going to include both the real and reactive power here. So I'm going to go and start recording information. And what points do I want to pick? I don't want any of my voltages. I don't care about those. I don't care about frequency. I want torque. I want, and you can pick whichever one you want. I1, I2, I3, they're all the same. So let's just pick the one physically in the middle, I2. I'm going to measure my DC value there. I want my speed. I also want my real power, P, and my reactive power, Q. And that's all the terms that I want. So now at 100 milliamps, I'm going to go ahead and record my values. Now I'm going to go ahead and tweak up and go up to 200 milliamps. So bring this up. And I can't get there from here, right? I'm only at 109. So what I'm going to do is I'm going to switch in another resistor because these two resistors in parallel is going to drop their effective resistance. And what do you know? I'm over. So I got to bring that back down. And this is kind of a little bit of a game where you got to try to switch things on and off to get close to your value. But this is the lowest that I can set it to with these two resistors in parallel. So 208 milliamps versus 100 milliamps, I'm okay with that. So go ahead and do my next recording. All right. And kind of notice what's happening here, right? We did 2 recordings where the field current was pretty big. Look at my actual current going into the motor. It's dropped quite a bit, but look at my torque. Hasn't really changed all that much. My power has changed a little. I've gone down about 18 watts, but look how much my reactive power has gone down. It's gone down a lot, right? It's gone down 100 bar. So let's keep going. So I'm at 200. Now I'm going to flip this switch and see how if I can get to 300. So I flipped that switch and I went from 208 to 308. I'm pretty comfortable with that. So I'm going to go ahead and record that value. And again, current has dropped, not quite as much as it did in the first case, but it has continued to drop here. My DC current, I'm controlling that, so it's definitely going up. Speed hasn't changed, torque hasn't changed, And the power has gone down a little bit, but hardly any, right? It's only gone down 9 or so watts. But again, I went from 297 to 228. I've dropped almost, let's see, what is that? 70 bars of reactive power. Now I'm going to see if I can adjust this and get to 400. Pretty good right there. So I'm going to record that data point. And again, current drops, torque's the same. Field current goes up, as we know. This has dropped now by 6 or so, but the reactive power has gone down by over 60. So keep going. Let's see if I've got... Can't get there from here. So what am I going to do? I can't get to 500 milliamps here. I'm stuck, right? With these 3 resistors in. So I'm going to turn this way for minimum current, and I'm going to short circuit this resistor, because no matter how many switches on I have, I can't get there from here. So I'm going to bypass it completely. So now I'm going to record my 500, my 600. Nope, I'm going to overshot a little bit. Pretty good with that. My 700. That looks good. My 800. Oh. Let's, for giggles, see if I can get to 900. I can. Close enough. And I'll just do the maximum that I can get. And I wouldn't probably do this in the real lab because I would really be pushing the equipment pretty hard. And there's my data points. So let me turn off the power because my machine is working pretty darn hard. Turn it off. Everything should settle down. Now, I'm going to go ahead and copy this into Excel. And let's bring that over here. And there's a bunch of different ways you can do it. In my personal opinion, there's a lot of heading information that is minorly useful. I typically find it's much easier to just do copy paste from here over to here. And I always leave the first row empty because I'm going to specify this is torque in Newton meters. This one here is armature current, or IA. This one here is IF. And I'll put amps DC and I'll put amps AC just so I really accentuate that. This is speed. This here is three-phase power, right, in watts. And this is three-phase Q, total power, in bars. And now I'm going to go ahead and do a plot. My first plot, hopefully, is going to look like a V curve. And I'm going to plot this current here relative to the armature current. So I'm going to go ahead and select this data. I'm going to insert an XY scatter plot. And I'll just pick this one for smooth fit. Let's see. So the data points are backwards, right? So let me select the data here. And I want my X values. So I want my sheet name here to be, let's call that IF versus, oops, IA. And my X values are going to be my field current because those are the ones I control. And my Y values are going to be my armature current. And Ladies and gentlemen, that to me looks like a V curve. I wasn't able to go up very far on this end. And the reason why I couldn't get very far is because the rheostat, the resistor that's in series with the excitation system, is really preventing me from going over there. But you can get a pretty good curve that goes down, reaches its minimum point, and then goes up. But I still could be wrong. I still could be getting invalid data. So let's go ahead. Well, first off, let's compare that to our curve here. So kind of looks like this, right? Maybe not quite as steep and going up as high, but if I compare the two, it's in the ballpark, right? You can see it comes down and starts to go up. It's just not as steep. And that might be that this field current is more compressed. So maybe there's more data points. I don't know. But it is a current of field current on the x-axis and motor line current on the right axis. Now let's take a look over here. We'll look at motor reactive power versus IF. So again, I'm going to do an XY scatter plot. Here's my X value. And I hold my control button while I select my data for my Q. I insert an XY scatter. And what do you know? It starts off positive at very little values of field current because the machine is very much underexcited. So it's pulling in a lot of reactive power to support the synchronous motor. As I increase the field current, I need less and less reactive power from the grid. More of it is coming from the fact that I'm more and more excited in my machine until I reach here, which is basically where I no longer need any reactive power, right? The field current is exactly what I need so that the machine can provide all. Once I continue to increase the field current, now I'm producing more reactive power than the machine needs, so I have to start exporting it. And so that's why the Q here becomes a negative number. It draws in reactive power until my excitation is almost 0.7, and then it starts to export reactive power, and so then it goes negative, which coincides with my V curve, because if you look here, right about at its lowest point, where the current is the minimum, it's where the reactive power is going to be the least. And then it starts to go back up again. Take a look over here. Look where Q is at its lowest value. Right here, this number. Well, look at the field, the actual, current, the armature current, 2.257. You can say, wait a minute, Paul, there's 0.233 that's lower. Well, you can see over here, right? This is -9. That's closer to 0 than this one. So actually, this one is kind of the lower value. Remember what we said, right around 0.7 or 700 milliamps? We can see that both in the V curve, and we can see that in this plot of reactive power versus field current. We'll also add one thing to this curve. If you look at the lab, it asks you to plot P and Q on the same chart. So here's my watts. My X values are going to be the field current, so it's the same thing. And my Y values are going to be watts here. And what do you see about watts? Well, the real power does, go down a little bit, but it's fairly constant, isn't it? I wouldn't say it's perfectly constant, but it doesn't deviate all that much. If you look at the actual data we have over here, it goes from 125.9 down to 92. So 126 to 92 is 34 difference, where when I compare that to my reactive power, it goes down from almost 400 down to -110. So you're talking over 500 bars of difference between the two, where the real power essentially has stayed constant. So our two curves here match what we see with these two curves. And with that, that's pretty much how to get through the parts of the lab. There are some questions to answer at the end of the lab. But I will pause the video here and give you a chance to collect data and do what you need to do, unless there are any questions. Any questions? Okay, do you all want me to leave something up before I pause the recording? Do you want the data that I've collected? Do you want the lab? Do you want the Excel plots? Do you want the physical setup, not physical setup, but the lab simulation setup in LVSim? You tell me what you all want.
When you recorded the values, then you were selecting the values from the metering.
Yes.
Um, I don't know how I couldn't get the column that you have that goes in the negative, like the Q values.
Yeah, if you remember, the way that I was able to do that is I had to keep increasing the field current. So I had to put the short across it, right? All three switches in the up position result in the minimum amount of resistance. Once I put the short here, I completely took that out, and then I could drive more current in there to get my negative Q value.
Okay.
Okay. Okay, what do you all want me to leave up? For information. Well, since nobody's got an opinion, how about I just leave this up? Actually, I'll put the Excel spreadsheet up, and if anybody wants me to put the other stuff up, just let me know. But with that, I will pause the video and we'll go from there.